At the beginning of the 20th century, physicists faced a serious crisis. Scientists had discovered the electron and the atomic nucleus, yet they still could not explain why atoms existed at all. According to classical physics, electrons orbiting a nucleus should continuously lose energy and collapse inward. If the laws of physics were correct, matter itself should be unstable. In 1913, a young Danish physicist named Niels Bohr proposed a bold new atomic model that combined classical ideas with emerging quantum theory. His work helped launch the modern age of quantum mechanics and change our understanding of matter forever. In the early 1900s, the picture of the atom was changing rapidly. J. Thomson had discovered the electron in 1897, proving that atoms contain smaller, charged particles. A few years later, Ernest Rutherford demonstrated that atoms possess a tiny, dense nucleus at their center. However, these discoveries created a serious problem. According to Maxwell's theory of electromagnetism, orbiting electrons should radiate energy continuously. If this happened, electrons would quickly spiral into the nucleus and atoms would collapse. Niels Bohr was born in Copenhagen, Denmark in 1885. His father was a respected physiology professor, and education played an important role in family life. Bohr showed exceptional talent in mathematics and science while still young. After completing his university studies in Copenhagen, he traveled to England to work with Ernest Rutherford at the Manchester University. A strange new idea was beginning to emerge. In 1900, Max Planck proposed that energy might be emitted in tiny packets called quanta. In 1905, Albert Einstein extended this idea while explaining the photoelectric effect, suggesting that light itself behaved like individual particles. These discoveries challenged the foundation of classical physics. Bohr realized that quantum ideas might provide the key to solving the mystery of atomic stability. In 1913, Bohr introduced a revolutionary model of the atom. He proposed that electrons could move only in certain allowed orbits around the nucleus. While occupying these special energy states, electrons would not lose energy and spiral inward. An electron could change energy only by jumping from one orbit to another. During these jumps, atoms emitted or absorbed specific amounts of light. For the first time, physicists had a model that explained why atoms were stable. One of the greatest achievements of Bohr's model was the explanation of hydrogen. When hydrogen gas is heated or electrically excited, it produces bright colored lines called a spectrum. Scientists had carefully measured these spectral lines for decades, but their origin remained mysterious. Bohr showed that the lines could be explained by electrons jumping between quantized energy levels. Bohr's success brought him international recognition. In Copenhagen, he established the Institute of Theoretical Physics, which soon became one of the world's leading centers of quantum research. Young scientists from across Europe traveled there to discuss the newest developments in physics. Though Bohr's model was revolutionary, it was not the final answer. The theory worked well for hydrogen, but struggled to explain more complicated atoms. During the 1920s, a new generation of physicists developed deeper forms of quantum mechanics. Electrons were no longer pictured as tiny planets orbiting the nucleus. Instead, the quantum world became far stranger, involving waves, probabilities, and uncertainty. During World War II, Denmark fell under Nazi occupation, forcing Bohr to flee the country. In 1943, he escaped to Sweden and eventually reached Britain and the United States. There he contributed to Allied atomic research connected with the Manhattan Project. After the war, Bohr became deeply concerned about the dangers of nuclear weapons and strongly supported international cooperation and peaceful use of atomic energy. Niels Bohr helped bridge the gap between classical physics and the strange new world of quantum mechanics. His atomic model solved critical scientific problems and opened the door to deeper theories about matter and energy. Today, quantum theory influences chemistry, electronics, computing, and many other technologies that shape modern life. Thank you for watching.